Alright, in section 2, we're talking about density curves and normal distributions. So I've broken this down into 2 videos. The first one, we're going to talk strictly about density curves. So we're only looking at the first 2 learning targets. Using a density curve to model distribution of quantitative data, and then identify the relative locations of the mean and median of a distribution from a density curve. We'll save the other 4 learning targets for the normal distributions video. So, in chapter 1, you kind of created a toolkit on graphical and numerical summaries for distributions. So, we talked about adding the same positive number or subtracting. You always plot your data, make a graph, usually it's a dot plot, simplot, or histogram. You look at the overall pattern, and then you calculate the numerical summaries. Then what we're going to add to this is step 4 here. When there's a regular overall pattern, we use a simplified model called a density curve to describe it. So a density curve has 2 characteristics. It is always above the horizontal axis, that's the x-axis, and the area underneath it is exactly 1. It's always, always, always 1. Okay? The area under the curve and above any interval of values on the horizontal axis estimates the proportion of all observations that fall in the interval. So a density curve is going to allow us to find areas, the area between 2 values, which corresponds to the proportion. Okay, so here example is about people's journey time, we'll say to work. So we have 2 intervals that they've broken up by color, 2 minutes to 4 minutes and 4 minutes to 5 minutes. So here what we have is a density curve model to represent this dot plot. It's essentially, as you can see, 2 rectangles. So they've broken up into 2 groups, the 2 minutes to 4 minutes, 4 minutes to 5 minutes. Now, 2 minutes to 5 minutes, this overall interval is 3 minutes. So remember, if the area of this rectangle is going to be 1, to be a density curve, the area has to be 1, well, that would make the height of the rectangle a third, so that the area, a third times 3 equals 1. Okay, density curves can come in all shapes and forms. It can be a triangle, rectangle, a composite figure, it can even be a curve. The point, though, is that the area has to be 1. So, the overall pattern of this dot plot of the amount of time it has taken Selena, as who it was, to get to the bookstore by train each day for the last 1,000 days she worked can be described by this horizontal line. That's the density curve. So, here we have an example of one that is an actual curve and not a line. So, the overall pattern of this histogram of the scores of 947 7th grade students in Gary, Indiana on the vocabulary part of the Iowa Test of Basic Skills, ITBS test, can be described by a smooth curve drawn through the tops of the bars. So you see this curve doesn't go on top of every bar, it kind of goes through some of them. What you need to understand, though, is that this curve is just an ideal curve of the data. Alright, so describing a density curve. We have the mean of the density curve and the median. So the mean would be if you were to balance the curve, half and half. Put it on a seesaw. Median is going to divide it in half. Okay, so the mean is going to take the values into consideration as weight and making sure that it's balanced, whereas the median is literally just taking, there's 50 data points, you put 25 on one side and 25 on the other. Alright, so in a perfectly symmetric, ideal world, the median and the mean are the exact same value, dead smack in the center. However, when you have a skewed right, your mean is pulled to the right a little. Think about that. If you have some values out here that are quite large in relation to the rest of the values, those are going to increase your average, which means the mean is going to be a little more than the median. Remember, the median, it doesn't matter what the values actually are, it's just breaking them in half. Okay, so for the symmetric curve, mean and median are the same. But for a skewed curve, the mean is pulled away from the median in the direction of the long tail. So a left skewed distribution, the mean would be less than the median. So again, a density curve is the idealized description of the data. It's not saying this exactly what the data looks like, but it's giving us a good idea. And we distinguish the mean and standard deviation of the density curve and the mean and standard deviation computed from the actual observations. Okay, so the mean and standard deviation from the curve could be slightly different than the mean and standard deviation of the actual observations, because this curve is just an ideal representation. The usual notation for the mean of a density curve is mu. It's a Greek letter, and then the standard deviation is sigma. So when we're talking about the statistics of data, we're going to start using these Greek symbols. So you have mu, and then you have sigma.